All right, well, thanks for those that joined us in person and online. We're thrilled to have our good friend and colleague, Dr. Antonio Ramirez, here as a guest presenter. He comes from the Welding Engineering program, and as we were just discussing, bringing us a topic a little outside of our normal day-to-day, but I'm sure we'll still find it interesting. So in addition to being a professor, Dr. Ramirez also leads the MAGIC NSF IUCRC, and so we've had some collaborations over the years across those spaces. With that, take it away, and thanks for joining us.
Okay, thank you very much. Thank you everybody for being here. I really appreciate it. It's horrible when you literally have to give a talk and there is like only 2 chairs occupied, so I appreciate you guys came. Trying to make this interesting for you. I'm not presenting anything about automotive industry today, but I do some work on automotive industry. I'm a joining guy, okay? And in joining, there is people who does modeling, people who does materials, science of joining, who does processes, who does like structural integrity of joining. I do material science of joining. Okay, so I'm a metallurgist, and that's what I do for living. So, but what I'm going to be talking today is how can we build things in space that are too large to be launched, or we want to start thinking on reusing materials that are already in space, or repurposing materials that is on other stellar bodies, and that's what this is going to be about. Okay, so this is a program we've been running for 4 years now, with the participation of different organizations listed here. It's OSU led, but we also have NASA and Air Force Research Lab working with us on this. Okay, so this is a very large thing. There's a lot of people working on this. I'm not going to get in detail, but we have Air Force people, NASA people. We're also working with Central State University. So we also have some historically Black university working with us. We have companies. One of the most important is Lincoln Electric, who we're working with. Everybody knows what Lincoln Electric is? Perfect. Great. And then the OSU people, I lead the team, but there's so many people involved. And actually, I want to give a special thanks to actually Dave Williams and John Horak, who manage Star Lab, and they've been very supportive for us. But we have other faculty, my colleague Boyd Panto from Welding Engineering, Alina City from ISE, other great collaborators. And we have a bunch of students, Kaweza postdoc, Eugene, Aaron, and Will are grad students working on this. They started working with us as an undergrad on a capstone. Okay, we also have Boyd working on this. I'm missing a few companies. So why this? Why is manufacturing space important or not? The past government considered yes. We have no idea what is going to happen tomorrow, but as a country, we think it's important. Okay, and there are some documents from the White House talking about that, and they want us to invest and develop technology for this. We actually, I wrote with some people in NASA on 22. We put a document for the National Academy of Sciences, telling them why it's so important to do material joining in space, how this should be done. So it's a little bit of that. Why we want to manufacture, we want to assemble, we want to service and repurpose assets on space. And it could be many different things about that. I'm going to talk about more about that. And we may want to use resources that are already in space. It could be resources that we put on space, or resources that nature put together on space, making planets or satellites, natural satellites. Okay. But we don't need these technologies like 20 or 30 years from now. We actually need these technologies now. They are just not ready. So there are companies being created to refuel satellites on space. And there is a company that actually has a contract to go on space, grab a satellite, and put more fuel back on it so they can keep running. So the space economy is growing very fast, and it goes way beyond SpaceX. There are so many other companies involved in this. SpaceX just happened to have a billionaire owner, so that makes things a little bit easier. Okay. Okay. Why we want a welding? Why we want a weld structures in space? For example, you're using resistance per welder in industry. That's very fast. Happens in milliseconds. Very easy, very efficient way to join materials. In a space, you can make very complex things. Rigidity. We can make joints that are extremely rigid, and that's quite important, and it's much better than adhesives. Adhesives in the space, the atomic oxygen, there is atomic oxygen on space, is pretty much its polymers. It takes time, but it does damage polymers quite badly. And adhesives, the joints you make with adhesives, they are not very tight. They could fail over time. Temperatures change dramatically in space over time. You are facing the sun or not, temperature change like 250 degrees C, that even more sometimes. So that's a problem for adhesives. They will leak at some point, so you cannot put humans inside a place that is actually closed with adhesives. Strengths, joints. When we join materials, we try to get very near to the original material strength. Sometimes we don't get it, but with certain joining process, we can get there. Much less mass. You're not adding anything else when you weld it. Sometimes we use consumables, but a lot of processes don't even use consumables. It's extremely reliable. Joints, when made correctly, welds, they last for a very long time. So it's much better than using, for example, screws that can get loose because of change of temperature and things like that. I talked about electricity already, and you've seen already on the space station, they have a micrometeorite came and hit a heat exchanger on the Russian model. They had a leak of gas. If they will have this technology, ready, they will have come out and fix it. Gas will be gone probably, but they will be able to send more gas and replace it. And we need this technology. You are going to Mars and something like that happens in the middle, there is no way back. There is no gas station to stop by and say, can you replace that tire for me? So this technology is absolutely needed for what we're doing. And let me give you an example. I know it's too many videos running there at the same time, but I actually have took the volume out, so I'm sorry about that. Okay.
Do you want to turn it down?
It is okay. How can I?
I can do that while you talk.
Okay. So let me give you an example. Fuel storage, refueling. So it's the video running on the center, and there are different companies doing it right now. The picture on the, it's okay. Thank you. Right there. There you go. I appreciate that. So we have in here, this is literally a module coming and refueling satellites. This is a company that already has contracts to actually refuel satellites. This is a European program. Right in the middle of the center, there's a European company actually trying to develop that as well. When you go to the moon, we need to build infrastructure on the moon, and maybe in a couple of decades on Mars, we need to start welding things in there as well, or repairing things in there. And this one here on the top left, this is the Air Force. They are developing a program where they actually collect sunlight with very high efficiency photovoltaics, and then they have a system that actually can irradiate, send radio frequency signal down, and you have a converter on land that you can produce electricity out of that. Okay, why that? Because you have people working. These are weird jobs. If you go to work, you are in a place where you have no resources, so you don't have to move fuel, things like that. That would be quite efficient. So they are trying to develop a system like that as well. Well, the size of the things that they need to make that viable is they are huge. They are humongous. Not everything can be just deployed out of like plastic, things like that. If we can build some of this structure in space, we'll be quite efficient. Remember, a lot of the things we launch to space, they are very strong because they have to survive the launch, several years during the launch. Once you put it on space, there is no weight, okay? There is no gravity. So you can make very long structures that are just going to stay in there. So it's quite efficient to actually be able to build things on space as well. So there are so many different necessities: defense, economic, and space exploration as well. So what happened is welding has been a very important part of the space program from the very beginning. And this is a very nice historical note when Von Braun was the guy who put Marshall together and run it and took us to the moon. So he had some other of his former colleagues from Germany working with him, and this very curious on managing some of the welding work for him, saying him and saying, I'm so sorry we have to bother you with all these welding problems we're having. And he answers to him, no, I don't mind about that. A lifetime of rockery has convinced me that welding is one of the most critical aspects for our whole job. Guess what? You go today to SpaceX, they're going to tell you the same thing. You go back to NASA, they're going to tell you exactly the same thing. Because what? A lot of the failures and problems they have are on joints. So this is a very important technology for them, and we keep working on that. What happened is, welding is, it looks like a spark. You think this is just a spark. It's very complex. You have like the whole process of metallurgy, from melting a material, solidifying, and getting to use, happens very fast, between seconds. And we are trying to get this material as strong as it was originally, and it was designed and was thermomechanical process. In welding, we don't have that luxury. So we have to be a lot more smart about that. So it's complex technology, and that's why we have a welding engineering program at Ohio State, okay? Because it's complex science behind this. Okay, so let's get back to space. When you are in space, these are the things that change: gravity, atmosphere, and temperature. So it depends on where you are, the different temperatures that you can vary, the different gravities, and the different vacuum levels. Depends if you are in deep space, you are in low orbit, you actually have different vacuum levels. Depends on where you are. When you are in deep space, you are ultra high vacuum. That's even very difficult to reproduce on Earth, but we can if we need. These things are very easy to reproduce on the lab. Gravity, there are different ways to do it. Okay, one is you can put your experiment on a parabolic flight. These tickets are expensive. You can use a drop tower, and for biological system, they use a random movement system where they kind of simulate a little bit of microgravity. It's not quite that. That doesn't work for the kind of experiments we use. Okay. And the thing is, what this makes, what happened is, all we know about materials processing and welding, everything has been benchmarked of experiments that we run on our lab now, under gravity, under regular thermal conditions, normally not under vacuum. Okay, so you will say, okay, just go into your models and make gravity zero, make pressure zero. Guess what? Our models were never calibrated for that, so we don't know if they're going to work or not. The only way to know if they will work is having data to compare with. That's the data we are trying to collect. Okay. So it's not new. People have been trying to do welding in space for a while. Okay. So the first ones to do parabolic flights, the Russians. Actually, they did the very first experiments on parabolic flights. The Russians in 1965. Okay, I wasn't born quite yet there. Okay. The first experiment was also the Russians on the Soyuz in '69. I was 1 year old at the time. Okay. The first American one was actually in the Skylab in '73. Guess what? Until last year, that was the last welding experiment the US had done. 51 years without doing almost anything. And what they did at that time was a very simple experiment. I will show you electron beam welding on space. We realized it does work, but it doesn't work the same as it works on Earth. That was a bit about it. Guess what? NASA managed to lose most of the data for these experiments. Okay? Because at that time was everything on paper and things like that. They do have some data, but not all the data from that. And that was expensive. More recently, so there are some other parabolics and other experiments happening on. We had an experiment that it was international, Ukraine, US, and Russia. We're going to do this on the Mir. It was flown. The astronauts say, no, we're not going to run it. It was electron beam as well. What happened is when you shoot electrons to metal or matter, you decelerate the electrons, they generate radiation, high energy one. So the astronauts were smart enough to say, we're not running this. Our clothes don't protect against that. So they didn't run it. More recently, then we have some other similar experiments like bracing. These bracing experiments are very tiny things, much easier to do inside a satellite. Microcube satellite. We recently, there's this company, Think Orbital, just put on a rocket another very small electron beam welding system, also the size of your cup. Okay. And now we just run a parabolic flight on others. I'm going to show you our experiment is just too large. The reason we're using a chamber we had, and then we are working with NASA to actually get this to space as soon as we can. So that's what we're trying. So let me give you some background. I told you about the Soyuz experiment. They did actually different processes. This is crazy. I have no idea how they did it, but this is the chamber where they run the experiments. This is the one on the Skylab. Okay, so we do have a little bit of information. Most important is it does behave differently, but it's doable and it works. And the mechanical performance is about the same. And this is the experiment that happened on the Skylab. Okay, everybody knows what the Skylab was. Okay, you see only the old heads are moving, as we have other space stations before. And the Skylab was the American one. Okay, I have to Google it as well. Okay, there you go. They later on, the Soyuz, as I told you, these guys, these Russians, I mean, they are great. This lady, I will not try to pronounce that name.
Savitskaya.
Say it again?
Savitskaya.
Savitskaya, I appreciate that. I'm going to record that later on so I can say it the next time. They actually went out, they went on a walk, they brought this torch, and they did some welding outside, okay, with electron beam again. And they were actually, as she was welding, the sparks that you see flying when it welds, they have to pick them in by hand and put it in because these things comes around again very fast, okay? So they actually, this was a several-hour walk, and they did this in outer space. I told you the one that was canceled in US that was going to be run on the moon, okay? So we wait for 51 years to put this out. For 51 years to run more experiments, and we are working with NASA and Air Force to make that happen. This, some examples of the things that were done at that time. Everybody is saying, is electron beam the one that should be? You have any idea what what is one of the most expensive things on space?
Power.
Power, exactly. Electron beam, you can actually run electron beam out of a battery, okay? The problem is it generates high energy X-rays. Okay, so if it's a robot, it will be okay, but will damage other things. So laser at that time wasn't a possibility. We used too much power. Lasers are getting better. Okay, so now laser is a viable technique, and you can use it for other things as well, like basic materials, inspection, things like that. A lot more difficult with electron beams, and that's what we are trying to do right now. Okay, so the status is success. We can use different processes. Okay, listed in there. And we tested this recently. I mean, this is our old slide, you realize. This was on August. We tested this on August last year. We show that it's doable. It works very similar, but there are some changes. There are some cracking that they couldn't identify what happened. They found difference on microstructure. Like the crystals are slightly different as well. So there are some questions. So this is going to affect the performance of the joints. Okay. What is the root cause physically to these differences? Some of them we can guess, but some of them is not very clear. Actually, I'm going to show you our current results. We haven't figured out what is different. Okay. The other thing that I mentioned to you guys, now we don't have to launch things. We can put them together over there. So we don't actually need an enormous strength. Unless we are building something that is going to land in another body and be launched again. That's different. Okay. And there are human operation challenges as well, like, for example, radiation and laser reflections. You get a reflection, and that's why we work on the lab. We have to use special glasses, special clothes as well, special walls to protect ourselves. Could be an issue as well. The other thing is, when you shine a laser in a material, any idea what happens? It is melting. What else is happening? Come on, guys.
Reflecting them.
Yes, you have reflection of light, absolutely. And besides that, it's very hot, then you have evaporation of material. And this is a vacuum. If you have air, then you create a plasma, actually, with the gas in the middle. Now this metal is evaporating very fast. What is that? That's a thruster. So now you start doing laser welding, you start moving things in space because you just create a thruster. So we are doing experiments with NASA on that as well. They have a special facility where it's a very flat floor, so we can actually measure that energy coming out from. So all these things have to be taken into account when we are looking into that. Okay, so that one I need the sound. How can I put it back on?
Go to that computer to exit out of the PowerPoint.
Sorry, exit the PowerPoint.
Yeah, the computer sound I turned down.
Oh, I got it. This is my colleague, Lloyd Fanzo, Welding engineer. He's the laser guy. That's not laser welding. That's gas metal welding. Okay, so what is our contribution? Okay, so we are trying to mature the TLL level. So welding in space is possible. That has been proven already. Okay, so we want to test how this goes. So we're creating instrumentation. We can collect a lot of data during our experiments, and then we can understand the weldability of these materials under space conditions. The space conditions I mentioned you which ones are the gravity, the vacuum, and the extreme temperatures. So we can actually go back to our models. I mean, it's not only in your area. When you get to welding and material science, we understand the physics so well. We can model almost everything. Not perfectly, but we can model things. We just need data so we can calibrate our models and figure out what is happening. Think about this. You're shining the laser, you're creating a whirlpool, the material is melting, and it's very hot, correct? This metal actually starts moving. There are different forces involved on that. One of them is buoyancy. It's gone. Not buoyancy anymore. Okay? So all these forces are changing, and all these things, how this is going to behave, how this is going to change. At the very end, they perform that job. So that's what we are trying to understand. So that's a laser well being made there. It's very fast. So we're going to be collecting all this data so we can at the end go and do all the modeling. So you see the modeling people is working with us already to see how we can actually benchmark these models better. Because today when NASA is going to weld something, the SpaceX is going to weld a piece that is going to launch, they do so many experiments, they try so many times, they get it right. Okay, at some point they get it right. In a space, first time, have to get it right at once. So we need very solid models. Because when the astronauts that are going to Mars are going to call us and say, by the way, we're having this problem, we need to fix this. You guys thankfully gave us this toolbox that will make the welds for us. Can you help us repair this? There's no way to do tests. We have to go ahead and model and give them a result within a few hours. That's what we are being prepared for. Okay, so this can be done. So that's the chamber we built for that. Okay, we can do vacuum, 10 to minus 5 torr. It's all dry vacuum. It's like low orbit vacuum inside the station when they open a pipe, for example. Okay, we can do variable gravity on a parabolic flight. We can change temperature with our chamber as well. No big deal for us to model that, but we still want to check. What happens is, for example, you get aluminum and you put it on very low temperatures, the thermal conductivity changes dramatically. It's not linear. So how is this going to affect as well? That's important. No one has cared about doing welding of aluminum at very low temperatures. We normally don't do that. So we need the data as well. Okay, we're collecting tons of data, thermal, imaging. You can imagine we are collecting it. It's important for us as well. And then now we're doing the post-weld analysis as well. So any idea how the parabolic flight works and why you get microgravity? Trying to explain.
Well, based on the position you are in the parabola, eventually you'll get to the point where like the aircraft starts to dive, and then at that point you have like the astronaut trainees or whoever's in there starts to float upwards and can simulate the microgravity environment.
Yeah, absolutely. So when the plane is going up, the plane is literally accelerating you together with it. And when the plane changes and start like turning back down, your body keeps going up. That's when you feel the microgravity. Okay, and only you, the whole thing that is on that plane, is feels the microgravity. It's that simple. Okay, but you only get like 10 seconds of microgravity, and the next 10 seconds you feel like you're going to throw up. Okay, because you're going from zero gravity to almost 2G within seconds. You actually, if you don't have experience as we don't, pilots do, you cannot even stand because it's 2G, it's not 1G anymore. Okay, so guess what? This experiment has to run by itself. We are there just to have fun and look at the computers to see what is going on. It has to run by itself. Okay, so this was all built by the OSU students, and that's the fun thing. This started as a capstone project. So we have capstone students helping us build this. So how fast you think this was moving, having capstone students doing it? Very slowly. So you have work with capstone students as well. It's just another course for them. Believe me. I mean, their head is, I'm looking for a job. I'm moving out of Ohio State. My life is going to start now. But we managed to get these guys so engaged. They help us, but we have engineers working with them as well. And some of the ideas and some of the work we have been doing. Something I want to show you is this here. So that's how our optics works. Of course, metal is evaporating. Now this is evaporation chamber. So everything is being covered in this metal that's redepositing, and it's being a problem for us on our optics. So now we're figuring out ways to control that better.
I got a question.
Yes, please.
How cold was that?
This wasn't cold yet.
Okay.
This wasn't cold yet. We are developing the liquid nitrogen system right now
Okay.
to be able to do that. Yeah, this was a room temperature.
Right.
Okay, thank you. Thank you for the question. And that's how the chamber looks inside. This is some of the welds that we did, and we are working on the model at the same time as well. This is the plates that we're putting. We are actually welding stainless steel, titanium alloys, and aluminum alloys, the most relevant ones for space applications. They do behave quite different. All the students working, that's a being made, actually at 10 to minus 2 torr to try to control the position. So that's how it goes. It's very simple. Laser is fixed, is the parts that work. Okay? We are doing workforce development at the same time. So we are at university anyway. We are here. We do a little bit of science, let's be honest. But our job here is educating you. That's our main job at the university. And when we are doing that, then we do some research on the side. Even we think we are all scientists. You really want to do science, go to a national lab. That's where they have the resources to do it. I come from one, so I can tell you it's quite different. So we have all these different custom students working with us with different impacts on the project. And the good thing is many of them are the graduate students working with us. Some of them we actually rehire them as engineers to work with us. I mean, let me give you an idea. Like this guy here, Grant. See, that he should be right here, the tall guy. The middle of the flight. Remember, between parabolas is like 3 minutes. Only 10 seconds, like 2 minutes, 10 seconds of microgravity. We're on the first parabola. Guess what happens? Microsoft, the computer crashes.
Oh.
Yes. First parabola. It's going to be, at that flight, it was going to be 40 parabolas. At that point, if it doesn't get back, you lose it. These guys, between parabolas, feeling like you feel really bad, he was able to go there and fix the problem with the software. We lose 2 parabolas. That was it. And that's possible because we build our own software. You will hire a company to do this. Most people do that. With that, you lose the whole thing. That flight is $100,000. Okay? So they have been instrumental. These guys are so smart. They work so hard. Right? Okay. These are the guys. That's on the plane itself. It is a lot of fun. If you have the opportunity to go. I will not go a second time. I feel bad by the time I came out. Commercial part. And you can feel my British accent. Okay, let's make this funny here. So that was the flight. We did with the experiments. We were flying with the NASA people as well and the Air Force as well. And that's right during the flight how it was going. So you realize more people there is just having fun. I was supposed to be on the back looking through the window. I don't remember a thing from that flight. Okay? I don't remember a thing. Okay. So how the data looks like. Okay, so I'm just going to show you one or two slides about this. So this is stainless steel. That's how the well looks from the side. This is we did computer tomography. These red dots, these are porosity. We do have porosity on welding, and depends how we do it. So this is the microgravity. This is on Earth. Okay, very similar, same conditions. You see, it's different. Okay. You will expect, because you don't have buoyancy, you will have more porosity or microgravity. That's not what we see. Okay. When we go to aluminum, and this is, we also forgot to say that, we also did lunar gravity. Now the NASA is very interested on the moon as well, but it's like 0.2%, like 20% of the air gravity, and Mars is like 40% of the air gravity. Okay. So we do have changes in there as well. When we go to aluminum, it's the opposite. Okay, so now we are modeling because we really don't know what it is. So it is not that obvious, like changing, making gravity zero in an equation, making temperature whatever you want in an equation is more complex than that, and that's what we are seeing. So we are working through this right now. These are some of the microstructures of this 316. So this is pulse laser welding. We do pulses and keep moving. So it's like think of this like a glass wine, and you cannot overlap them. That's how it looks like. And so this is like the first glass wine. This is the second that is slightly overlapping. And the solidification changes. We solidify so fast on this process. We change solidification mode. That means it may crack. And initially we thought these were all cracks. So we went to the SEM. There are no cracks. There's something else going on. And now we understand if this is going to change the solidification mode as well. It's going to change the crystallography. May this have any effect on performance? We don't know. But I'm a metallurgist. I'm more interested in the science than the final performance at the end. I have to be honest. Okay, performance will pay my bill, but I'm more interested in what happens with the crystals in there. So we've done this. We created instrumentation. We can run it. We are running, reproducing the space conditions, and now we're working to go here. We keep working in this for a while, and now we're working within something around $5 million to be able to build a smaller experiment that we can send to the ISS to do longer time experiments over there and be more relevant. Okay? So that's what we did in August, our parabolic flight. We are changing some things to improve. I'm doing some other things we didn't have time. We have two other flights, one in May and the other one in October this year. We're also exploring other processes. Okay, and we just got some money from the college, and we applied for money from the university just to design a system to go to space. Because we need a pre-design so we can go to the agency and say, give me $4 or $5 million to build this. So we are working with them on that as well. Okay. That's where we stand. Okay. NASA is also building a smaller chamber, so we are supporting NASA Marshall at the same time. They are building a small chamber. They're going to put on a rocket to do a very short laser welding experiment in space very soon, within a few months. They are learning from us. They're seeing everything that went wrong with us, so they don't do this very same mistakes. So it's been instrumental for them as well. And now we are working with NASA, ISS, Air Force, to develop the payload to go to space. That takes a lot of money, okay? And we literally, when I say 5 or 6 million, we have no idea how much it's going to cost. And this doesn't include the ticket to get to space. It's just to build instrumentation that is certified to go to space, okay? The flight could be, we could go to the space station before they retire. It's going to be very soon, 2030, my understanding. That may change. But you realize that the Russian part of the station is literally falling apart. Okay, they haven't been able to maintain it properly, so it is a risk, a very high risk. But there are some instrumentation of the ISS they are trying to use, and you realize, for example, the Europeans just flown a laser system to duality on space. We contact them and say, "Can we use your laser?" No, we can only work with European. So we are trying to work through NASA to get access to that, so we don't have to fly all the thing. So politics goes everywhere, and we are trying to put all the things together for that. The future will be, we need to get into robotics. It's not people doing this, it's going to be robots. And then we have to involve other organizations to make that possible. There is a national lab already working on robots for this kind of work on space, okay? My friend, Boy Panton and myself, we just created a company, getting in trouble with OSU, of course, because we created a company to try to actually move this much faster so we can compete with these other guys. Otherwise, they're going to eat us alive. And we are the ones actually creating the data that everybody needs. And we are trying to work out partnerships with large companies to make this happen. With this, my question is, are we on the right path? So this program, this didn't happen, unfortunately. This was just canceled on September last year, where they're going to be put a satellite that will do some manufacturing process on space. This may change, but it was killed. It was recently killed, the program for that. So are we going to do this, or are we going to enable this? That's my question. Our budget is tiny compared with the budget that, for example, the Chinese have to make this happen. And money here is document, guys. I mean, if I will have the $5 million today, we'll be designing the system to go to the ISS already, or we'll be flying in a year from now. But my problem is 80% of my time is trying to find that money. Okay, so we need to make a difference here, and hopefully, with even all the craziness that is going on right now in our country, probably this some of these things will change. And this is where we want to be very needed. And this looks like science fiction, but this is exactly where we want to get.
Yes. Space station.
With welding, we can build things of that size. I don't know who's going to launch the materials, but we can build it. And don't ask me if I got the permission from Disney to show this. Okay, but it's just a beautiful thing. This is all the people who work on this, all the funding that we have from different agencies. So I have to do that, and we say that will say thank you for your attention, and I really hope it was worth your time. Thank you. So I'm happy to answer any questions you may have. Yes, please.
Can you go back to slide 17?
Oh, God. I'm pretty sure it's a difficult question, correct?
I was very interested in the top image where you show like simulation like that.
This one?
That one. Is that like a electrical model of?
Yes, so we had to redo all the, so what happened is this original chamber was a different experiment from NASA. That's why it's so large. We built the chamber. And we have to redo all the electronics and electric part of it. And I'm no electrician, so I have no idea. Sarah, the lady who was speaking on the video, she's the one who did this. So this is capstone students making this happen. The thing is, this is going to be on an airplane, so every single screw that we put in there was FAA approved. The package of documents that we have to submit to be able to fly with this was like 2,000 and something pages. Every single thing had to be calculated. All the stresses on the structure is crazy. So this, even if it was an undergrad student doing this, they got this certified to FAA. Beautiful work. Don't ask me details, please. I have no idea how that works.
No,
I know I get
that's not
110 when I
cool.
need it. Please.
How different are the actual weld parameters? Do you kind of start with the parameters you would use on Earth and modify from there, or is it just a totally different development process?
We don't know yet.
Okay.
We really don't know yet. For example, I forgot to put a slide. So we have a sparks coming up. And we clearly see from our videos, and we're using software to track them, that we have sparks and microgravity, of course, going straight, the other ones not. So now we can use these videos. We're going to use cameras in 2 different directions so we can track in 3 dimensions. And with that, we can actually measure the impulse these particles are coming out. That's, but a stop flying out on space is always a big problem. So that has to be addressed. We know in laser welding how to do that. Our pulses were square in power. Now you can change, like tamper the power, how it goes up or goes down, and we can eliminate the sparks. We know how to do that on air. Is it going to work the same on microgravity? We don't know, but we'll test that. Any other question? Please, sir.
Thanks for that was good. So it's an engineering question. Do you have to design around the amount of power you're allowed to use?
Yes.
You have to design the experiment for the power outlet.
Yes. And the plane is more forgiving. We actually have a lot of
I'm
power.
talking about an orbital.
Yes,
experiment,
we
yeah.
do, and we're working on that already. So we know how much power is available on the place. So the power in the space station is not the same everywhere.
Yeah.
Depends on the model that you are. You have different. It's probably the electrical circuit is different. So in certain regions there is more power than others. So we know the power that we have. Our first calculations are literally on a spreadsheet, and we know we have enough power to run the experiment, but we have to rebuild it. It has to be much smaller. Our laser is 1.5 kilowatt. Probably over there we have to take a 1 kilowatt laser. We just have to scale down our experiment a little bit to be able to still reproduce the right physics.
So
But it's doable.
you can design the model power requirements for the space station,
Yes.
and then integrate that into a future experiment on another lab.
So we are thinking about that already. We are trying to design our experiment in such a way
Yeah.
that we can put it on a different space station with boy later soon. But the problem is no one knows how these other space stations are going to work. They are building the space stations. It's like when you're putting a building for a new lab, but no one has any idea how the lab is going to work. It's the same in space right now. No one knows. Like how is Boyer going to sell time or host facilities is not defined. So we still have to try to get the ISS. There is a facility there where we can run our experiment. We have to modify it. So we actually just got money from the college, and we're waiting to get money, a little bit of money from the university to do a preliminary design and make all these calculations that you asked, and especially get a budget. And building things for space is not us. We have to work with a company who can make something. The certification we got was easy peasy. For space is different. So we cannot manage that ourselves. Maybe a center like car. So this is something where when we get to that point, we are doing some of these things with CDME. You guys have some expertise that we may be able to actually leverage for something like this. I'm a scientist, man. I'm not an engineer anymore. So when it comes to do real things that work, I struggle. Okay. Any other question, please?
Antonio, is that a comparison for this simulation? What is the result?
Yeah, this is a very poor simulation. We're just getting started. But yes, this is the first trial I tried to simulate this. This is still just thermal. Now we just pour a piece of software, we can do the fluid dynamics. And Alina City, the guy who talked about the video, is going to do all the fluid dynamics, and then we can incorporate better things. So the way they're going to do is pretty nice. We actually do most of the physics on fluid dynamics, but these simulations are so expensive, computationally expensive. You cannot even run a whole well.
Which type of software are you using?
A 3D flow.
Okay.
3D flow. So they simulate, they get the shape of the well pool, and what is the temperature on that edge? The melting temperature of the material. You get that and you put in the other model, the finite element model, now you can model the whole thing. That's how we're going to do it. And we are waiting to hear from NASA if it survives, to get $1 million to start doing that series model. Yes.
So Welding Institute question. Over there, you have a laser MIG hand welder,
We do.
right?
Yes.
And it's got a gas. Use a gas for that. gas shield.
Shielding us.
Yeah, but it's a manual, you can, hold it. Do you
Yes.
think that's possible in orbit to use for an astronaut to do something like that?
Absolutely, but that thing is dangerous anyway. Okay, speckle reflections could be very dangerous because you have a speckle reflection going to a wall can make a hole on that wall, and that happens on our labs as well. So we have to be careful. These systems have the protection. They have a capacitor sensor, so if it's not touching the surface, it
It's
doesn't.
got a tip on it, you gotta, yeah, I've seen it over there.
So that is possible. So we have two of these handheld laser well systems on our lab. I used to work on a synchrotron lab. So a former friend who now works in Europe building another facility, we talk all the time. He's my vacuum guy and he's welding guy. So he called me and said, I'm doing this. I said, you need to use a handheld laser. I said, that's your solution. He said, perfect. He bought it. Safety people came in and said, you need to trash that thing.
It wouldn't be,
You cannot use that here.
it wouldn't be used by humans, but the machine that you have over there could be modified to be robot controlled, those little critters you had wandering around.
Absolutely.
They would be the ones using it.
That's what we're trying to do. That's where at some point we'll be just a laser, and that's how it works in industry. It's a robot who actually is holding the laser head and doing the laser welding. Laser welding is used everywhere in industry. Okay? And we know how it works very well. Okay. Any other question? So thank you guys. Thank you very much for staying this long.
Thank you for coming.
Thank you for inviting me.